and good evening. Thank you for joining in. It is lovely to see so many of you already here. Let's wait for another minute because I can see a lot of you are still joining in. While we wait, all right. While we wait, let me quickly confirm that everything is working on your end. If you can type yes in the chat to confirm that my screen is visible and I am audible, that would be really helpful. Wonderful. Thank you. Welcome, everyone. We have a genuinely interesting session lined up for today. The topic is right in front of you. Today, we will look at how Retrieval-Augmented Generation, usually shortened to RAG, helps a language model gives accurate, grounded answer for your own data rather than guessing. And instead of staying at the level of theory, Sharit will build a working AI application live using LangChain so you can see the whole thing come together at the end. Uh, Before we begin, a quick word about who we are. For those of you who are joining for us for the first time, Interview Kickstart is an upskilling platform for technology professionals. We help you in two ways. We help you add the latest AI skill to your current role, and we help you prepare for and clear interview at the top technology companies. We have been doing this for more than 12 years now. We started in 2014 in Silicon Valley, and we brought the program to India a few years ago. We are frankly obsessed with the technical professionals, and we do not treat everyone the same. We run 18 different tracks built for different roles, and I will come back to that later in the session. Our real strength is our faculty. We have more than 700 instructors who are practicing AI professionals in their day jobs at companies such as Google, Amazon, Netflix, Tesla, and Microsoft, and many others. They are hiring managers, they are senior managers, and they spend their time on weekends teaching that what actually current AI and is doing in the real world and in interviews, how exactly you have to go out. More than 27,000 professionals have already been through our program. And that brings me to our instructor for today. I'm super excited to introduce Shurit Deshmukh. Let me tell you a little about Shurit. Shurit holds a PhD in computational modeling from MIT. Today, he is the director of machine learning at Infinite Cooling, an MIT founded climate tech startup where he leads deep learning and generative AI work from ground up. Before that, he has worked on machine learning at TikTok, on e-commerce recommendations and marketplace optimization. And he has also been a machine learning research scientist in industry. He reviews for several engineering journals, and he is known for a strong data-centric approach to building machine learning systems. In short, this is someone who builds and ships these systems for a living. Sharit, thank you for joining us. Before I hand over, I would like to know this room a little better. I'm quickly launching a poll now. I want to understand three things from everyone: who you are, what you are targeting this year in your career, and what exactly is standing between you and your goal. Please take a few seconds to answer. The more honest answer you give, the better I will be able to tailor later on in this session. Sharid, over to you. Have a good one.
Thanks, Mohit, for the kind introduction. A quick check. Can folks hear me okay? Okay, perfect. And can folks see I'm gonna share my screen. I'm gonna take over the screen share, Mohit.
Sure, Sharid. Just give me 1 second. I will stop my screen.
Okay. I think, can folks see my screen okay? Okay. Thanks, everybody. Let me go into slideshow mode. Great. So today we'll be talking about Introduction to Retrieval-Augmented Generation, or as it's often called, RAG. But before we talk about RAG, we are going to talk about what are the important pieces that make a RAG-based system work. So, for example, a RAG-based system typically has a few components, right? One of them obviously is a large language model to do the uh, understanding of the user query, summarizing the output, and finally generating the response. But beyond just a simple LLM, in a RAG-based setting, you also have multiple other infrastructure that you need to assemble. For example, specifically for RAG, you have something known as a vector database. You need to store your information, the information that you want to retrieve in a vector database. So that's a infrastructure cost or overhead that you need to account for. What do you do with that vector DB? You need vector embeddings to go into this. And so you essentially generate these vector embeddings and you do an embedding model for this. So we'll talk a little bit about that. Then we'll build a working RAG pipeline with LangChain. So there are multiple agentic frameworks like LangChain, LangGraph, Crew AI, N8, and Zapier, and so on, which you can use to build a RAG-based pipeline. And I'll show you how you can quickly debug and optimize your RAG-based system, and then show you a working demo towards the very end. So that's the agenda for today. So why retrieval augmented generation? So the field of Gen AI, LLM, machine learning is moving at a breakneck pace. And in the era of generative AI, integrating search is imperative to ground your large language models with factual context. So imagine a scenario where you take a pre-trained language model. I'm not talking about GPT or I'm not talking about Chat GPT or Claude and so on. I'm talking about a pre-trained large language model. Can someone mention in the chat what would happen if I ask this pre-trained large language model, what is the current weather in Bangalore? What would a pre-trained large language model do if I ask it about the current weather in Bangalore, or any city for that matter? Um, it will hallucinate, right? It will essentially give a random reply. It will give um, like not the current weather answer, and um, those are all like problematic cases. What it might also do is it might not like it might give a very reasonable sounding answer. It might say something like, oh, the weather in Bangalore is something something degrees Celsius and cloudy, because it has learned that a answer to a question like what is the weather in some city should be followed by a grammatical structure like so and so. So that is the issue with LLMs and hallucination. This is actually worse off than saying something like I don't know, right? Because I don't know is actually a very acceptable answer in this particular situation. I don't know the current weather in Bangalore because I don't have access to tools or weather API and so on. And it might not do that. Retrieval augmented generation is one paradigm that you can use to ground the LLMs in context. So RAG lets LLMs access external data, reducing hallucinations and enabling domain-specific knowledge. Why are all of these words important? So what is external data? You maintain this vector database, right? Where you store all the information. That's your external data. You tell your RAG-based system to match the user query to um, to the information in the vector DB. And that's your reducing hallucination part. And enabling domain-specific knowledge essentially means, imagine you have a situation where the large language model was not trained on this specific information. There's no way for a large language model to know some specific questions, let's say, about your company. So how can you make this LLM answer specific questions about your company policies, and so on? You need to give it some context, some external context. And that's where this domain specific knowledge embedding in a vector DB comes into play. Um, AI chatbots, assistants, recommendation systems widely use RAG-based systems to provide accurate and up-to-date information. This is just saying that because RAG-based systems typically have a memory refresh, what I mean is you can always update the documents inside the vector DB on a periodic basis. And so that essentially makes the information be up to date. So why does we talked about all of these things in a way on the previous slide, right? Why does RAG matter? Because it provides concrete factual information which is grounded in specific sources. And so that enhances accuracy. It provides dynamic knowledge updates, so you can always refresh the documents that are a part of your vector DB, and domain expertise. Even if the base large language model was not trained on a specific domain, let's just say you want to create a chatbot that answers question about anything and everything related to your company. Um, no large language model is trained on the internal information for a particular company, right? And so what are the ways to actually make a model like Opus 4.8 or even Fable 5 or whatever answer questions about your company specific documents? You need to give it access to some external knowledge, or what it needs to build that domain expertise in for your company documents. And so the way you build that domain expertise is you transform these general models into specialized knowledge workers for these specific applications. And RAG enables you to do that, right? RAG is again just one paradigm that enables you to do that. There are some other options like fine tuning, agentic frameworks, give it access to multiple tools. Um, RAG is one such option. So before we dive deep into RAG, let's ask a let's understand the simple concept of how multiple pieces come together. A user asks a question. That question comes into the LLM. The very first thing that a in a normal setting, what the LLM will do is it will go back into its pre-trained knowledge. It will look at the neural network weights. It will adjust the weights such that it will see, oh, okay, if this is the question, what is the most likely response associated with this particular question? And it will start generating that response. Um, that's a normal LLM scenario. In a RAG-based setting, a user asks question. That question is first searched in your vector DB knowledge base. So what that means is that let's say a user asks a question, what is the latest news in the world of in the world of sports as of yesterday? Let's say our vector DB stores all the sports related news up until this morning, and it refreshes at 9 a.m. every morning. So a user query now has access to what happened in the sports world as of yesterday, right? Because we have refreshed up until the latest news up until today morning 9 a.m. So this user query then gets compared to a knowledge database, and it finds, okay, this user is asking about cricket for yesterday's match and so and so. Let me see which piece of information is most relevant for this particular user query. And let me retrieve those pieces of news articles and attach those to the user query and enhance the prompt with all of this context. So not just the plain simple user query, but all of this extra knowledge, this external documentation that I retrieved. Let me augment the prompt. So that's where the retrieval, so this query knowledge base, this part is the retrieval part. Enhancing the prompt with retrieved context is the augmentation part. So this is R, this is A, and then you combine these two blocks to then send an LLM to then send this entire context to the LLM to generate a response based on this entire context, not just the user prompt. So that's the retrieval augmented generation part. Okay. And there are a few ways to do this. We can do multi-shot prompting, where essentially we send in context examples to the LLM and have the LLM guide the model's responses. Tool integration is one where you enable LLM to call back into code and run some supplementary functions. Basically, in my sports example, what if I just give it um, um, Google News API or something, right? That way there's no need for RAG. It can just call that API and get the response. But now you are factoring in API costs. So you see how the unit economics of this is already starting to play out. You will have to make a decision that way. And finally, additional context where relevant information directly lives in the system prompts. Um, the work that we are going to um, the demo that we are going to do today is going to have an example which works with a knowledge-based structure of a company. So we have some company documents, we have some contracts, we have some employees, we have products, and we are going to be asking questions around these four different types of documents and the content within those documents. Um, Typically, one way to reduce hallucination in LLMs is to create a high-level system design prompt. Typically, system prompts have a higher order of preference, if you will, than user input query. And a system prompt tells the LLM that, okay, these are the instructions that I need to follow first. These supersede the user level prompt. So a system prompt is saying something like, you are an expert in answering accurate questions about insurance LM, the insurance tech company. Give accurate answers. If you don't know the answer, say so, don't make anything up. This instruction is one of the critical ways for mitigating AI hallucinations and making sure that the system is answering only questions about your particular use case right now. And it guides I mean, this is just one line system prompt. In production, you'll have like a multiple paragraphs of system prompts for multiple different aspects that you are trying to put a guardrail against. Um, these types of prompts guide the model towards a factual response. It helps the model avoid generating random responses, and therefore then, as a result, enhances the user trust and reliability of the model as a whole. So given what we have talked so far, can someone mention in the chat, in a RAG-based system, why do we retrieve document chunks before generating an answer? Is it A, B, C, D? Okay, so there's a mix of responses. It's essentially to help the model use external knowledge not stored in the parameters, right? To reduce the why is number one not true? It's not true because if you retrieve the context, which is very large, number of tokens is going to be very large. Um, Embedding size and what is retrieved in RAG are two different things. They're orthogonal in a way. Converting all text to SQL queries is just one application, let's say, of a RAG-based system. You can store a bunch of common like question to SQL queries and retrieve them from the vector DB, but that's just an application. What RAG really, oh, um, what RAG really does is that it helps the model answer questions using external knowledge. So now that we know what a RAG-based system is, let's just talk about what vector embeddings are. Um, Vector embeddings transform this language data into a fixed mathematical representation of text-based information, or not only text, but even image-based information, documents, video, audio-based information into a mathematical vector that represents that information. So for example, think about a statement like car insurance, vehicle insurance, and automobile insurance. If you do a simple keyword-based or string-based matching for this scenario, car, vehicle, and automobile don't have a huge overlap in their strings, right? Or in their characters, the way they are constructed. So how would you how would you let the LLM know that when I talk about car, vehicle, automobile, insurance, they all kind of mean the same thing? And that's where semantic understanding, this concept of semantic understanding comes into play. What that means is that you convert your input data into a mathematical representation, uh, let's say a mathematical vector, and you store those vectors, a list of numbers essentially, into a vector database. And as a result of this, what you can do is you can ask similarity questions on this text-based information that does not rely on keyword-based searching. So one of the properties of vector database is that things that are close together in semantic meaning, not just keyword-based meaning, but semantic, which means that hold this car, insurance, vehicle, automobile insurance, all of these words, all of these concepts will live together in the vector DB. Some other concepts which are not relevant to car, vehicle, auto might live in some, like, let's say there's um, home insurance, property insurance, flood insurance that might live in a separate section, but still within a cluster in this vector DB. And so as a important piece of a RAG architecture, these vector embeddings enable our LLM or AI systems to retrieve these semantically relevant information from knowledge bases. And therefore, the LLMs can ensure more precise and hallucination-free responses. Um, so vector embeddings, as I said, are converting is a they typically convert text or any other modality, not just text, but um, input data into a series of numbers representing some meaning in a high dimensional space. And in the demo, we'll be using OpenAI embeddings, which converts your input data into 1536 dimensional vector. And it can have a variety of different input types, so like characters, words, sentences, complete documents, abstract concepts, and so on. And why does this thing work again? Semantic relationships work because you can do mathematical operations on them. Because if I ask you generally, what is this equation, which is you take king, remove man from it, and add women to it, what is um, what is the result of such what is the result of such equation? There is no meaningful way to subtract the word man from the word king, right? I mean, what does that even mean? But if you think about it in a semantic fashion, king represents a ruler whose gender is a male. If you are going to remove the gender aspect from the word king, but add or remove the male gender, but add a female gender to this concept of a ruler, what would that be? That would be queen, right? And so these are the types of operations that you can do to these vectors. So for example, the king vector is here, the woman vector is here. If you like take this thing and the man vector is here, so if you take this minus the man, it will be pointing towards this direction, and so that's your uh, queen vector essentially. So just to complete the picture from our previous thing, we convert our input query into this vector embedding. This vector embedding now gets looked up in the vector DB to see which vectors are closest in meaning using this previous method like this. Do folks know some of the similarity metrics that are used to Have folks, KNN is K nearest neighbors, yes, but how do you compare it if two vectors are similar or not? Have folks heard of cosine similarity? Exactly. So as some of you are saying, right. So cosine similarity is one way. There's other similarity measures as well, but so that essentially is used to search the vector DBs, and then we retrieve the original documents which are most similar to the user query vector. And then this is your retrieval again, this is your augmentation part, and this is the generation part. So we will be using LangChain towards the end to build this demo. LangChain is one agentic framework. There are multiple other frameworks like LangGraph, CrewAI, and all of them have different strengths. LangChain helps you make apps relatively quickly. They have easy integration, easy SDK to work with multiple databases, APIs, and vector DBs. Supports memory chaining and agentic framework to make deployment of these apps a bit more uh, seamless. LangChain offers a lot of integrations with a variety of LLM providers, and so you don't need to worry about changing your underlying. They themselves update their packages very, very frequently, but you don't need to worry about changing the model every single time because they have integrations with a variety of different providers. So you can choose OpenAI's models today and Google models tomorrow and Anthropic's models on the third day, but and the underlying code might be underlying code will stay mostly the same. So some of the advantages are quick go-to-market strategy, standardizing RAG workflows, model agnostic wrappers, and generally it's medium code framework. It's not too verbose. It's not as no code framework as N8N. It's not a drag and drop thing, but with a few lines of code, you can get a working piece ready. Um, but because the APIs keep maturing over time, you still need to keep a track. You have to do a very strong version tracking and dependency management. So some of the like if you keep the code stale for a long time, there's a high chance that some of the imports might not work because they have updated their syntax or so on. Um, but still, it gives you a very strong head start. So one thing that we will look at is document loading with LangChain. So how do you transform static files into chunks? You cannot load an entire document into the LLM. Can folks mention why? Because let's say I have 1,000 documents. Each of the document, let's say, has 1,000 words. Within those 1,000 words, um, each of them, let's say, is around 4 words per 4 tokens per word. So 4,000 tokens times 1,000 documents um, is more than 1 million tokens, right? What is the state of the art context length for these state of the art LLMs? It's around 1 million, right? It's you are going to like overshoot the context length very quickly. So you need to have a method where you can say, based on these, based on the, I'm going to take a document and I'm going to break that document down into small chunks, add some metadata associated with that document to these chunks, and then create these document objects that the LLM can retrieve small piece one at a time, which is most relevant to the user query at hand. Typically, when a question is asked, seldom will you require an entire document of 1,000 pages to answer that question. Typically, you would need only a specific piece within that document. And so one way to do so is of having a chunking strategy. Chunking, in long story short, as the name suggests, it really means just taking a document and breaking it down into smaller pieces. So you take a 1,000 page document, and let's say if that document has a very nice page structure where one page means one thing, maybe a page-based chunking strategy is what you need. If the document has no structure, maybe this recursive chunking strategy, like um, some particular characters per chunk is what you use. So there are multiple different chunking strategies, but um, long story short here is that you take your document, break them down into multiple chunks, and those chunks are then converted to these vectors that we talked about and then stored in the vector DB. And so when you retrieve a semantically similar vector, you are retrieving these smaller embeddings that represent a small portion of the document, or a chunk or a few chunks in that document, as opposed to this entire document. And that helps you manage context then as well, right? So we are going to use OpenAI embeddings. Again, as I said, it has 1536 dimensional vector output that it gives. So each chunk becomes a point in a high dimensional space that we can store in our vector DB. And what we can do is we can use this semantic similarity to ask questions like, if a user asks questions about vehicle insurance, but our document says car insurance or automobile insurance, those documents will get retrieved because semantically speaking, car, vehicle, and auto are the same thing, are similar thing. So here's a quiz. If two text passages have similar embeddings, what does that usually mean? Right. As most of you are saying, it basically means that they are similar in meaning, right? And they don't live on the same database row. They live in the same database cluster, or similar database cluster. So the next thing that I want to talk about is vector DB. So there are multiple different vector DB providers. Some of the open source ones that I'm familiar with are ChromaDB. It facilitates storage of these embeddings, semantic search on top of them, and as a simplified API. Some other options that you can use are Qdrant. Pinecone is an enterprise solution where they have a paid license that enables you to have these security features, role-based access control, OAuth type of authentication, and so on. I think Chroma also is adding those features as time goes on, but this is one open source DB, vector DB. Another one is FAISS, Facebook AI Similarity Search. They have their DB as well. So if you choose ChromaDB, all that you need to do to convert these vectors and store them as vector embeddings into a DB is just like take those chunks, take those embeddings, and create a vector DB. And this straightforward API essentially creates a vector DB that you can then use as a part of your RAG-based system. And as I mentioned, humans can think visually in three dimensions at the most, right? Beyond three dimensions, visually speaking, uh, it's hard to represent information or even imagine information beyond three dimensions. So one way to visualize these high dimensional vectors is to collapse them into a 2D or a 3D space. And so as you can see, these orange dots, each of these dots are a chunk. They might mean all the documents associated with vehicle insurance. All of these orange dots might be documents associated with, let's say, home insurance. All of these green dots might be employee or product information associated with the company, and so on. So each color represents a document type or content, showing how similar in content they are. And so they naturally sit closer together. And these clusters then can reveal meaning, right? So for example, all the employees can be in one cluster, all the contracts can be in another cluster, some products that the company offers can be the third cluster, and some company specific policy information can be in fourth cluster, and so on. ChromaDB is one way. Let's say again tomorrow you decide you want to use a different vector DB like FAIS. That is again possible. In memory storage, it has GPU, CPU variants. And again, because LangChain has integrations with all of these LLM providers, vector DB providers, minimal code changes from previous code. So for example, it would basically be like a few lines of change. So this chroma db object has a from documents method. Once you generate this vector db, the downstream code can still look entirely the same. Okay. Um, Another quick quiz. What is a vector DB mainly used for? Correct. So it's, as we saw, it's specifically designed for similarity search. It stores these vectors or embeddings and helps find items whose vectors are close to the query vector. And why might a company use metadata filters in a vector DB? Correct. So even if you store the entire documents, you can help the vector DB to make the search even more efficient by like tagging some metadata which says that, okay, all of these 1,000 chunks are about this document. All of these next 1,000 chunks are about this document, and so on. So that essentially you can leverage a hierarchical index within the vector DB that says, okay, a RAG system gets a question. The question is about company policies. So all the remaining clusters about products, HR information, employee information are not even searched. You go through the metadata and identify which documents are labeled as a company policy and only search within those documents, right? So it enables like this very um, fast search amongst relevant subset of the entire documents that we have. So that's the pieces that I wanted to assemble. I want to hand over back to Mohit, and then we'll go and look at the demo towards the end.
Thank you, Sharit. Let me share my screen. While while Sharit gets next part ready, let me use these minutes well. Just a moment, let me share my screen. Sharit, can you confirm if my screen is visible?
Oh yeah, it's visible.
One moment. All right, Sharit, I will need your help once more to confirm if my screen is visible.
Mm. Uh, yes, visible now.
Lovely. All right. Okay. Two quick things are coming up. First finish. We'll first finish the build and see that working application. We'll also cover how you would answer questions on what should it just showed you, the way they actually come up in interviews. That's the second part, and that matters because that is exactly how we structure our programs. We teach the concept and then we teach you how to defend that in a particular room, in the interview room. Thank you for answering the polls earlier. It told me two things about this room. The first is that most of you, around 63%, wants to add AI skill to your current role. You have spent years earning a strong technical foundation. You want to build on it, not start over. The second is what is holding you back. And the most common answer, around 54% to be precise, was simply not having a clear roadmap. So let me spend next few minutes on exactly that. Let me show you how we think about becoming a 10 time more effective professional in this AI era. See, when senior professionals like you with AI sit with AI, most of them feel one of the four things. We call these four stages of AI denial. The first is AI is moving too fast for me, as you can see. The second is my job is unique, so it is safe. In 2016, I think we can agree that no role is fully insulated. The third is there's simply too much out there and I do not know where to start. The most common one. And the fourth, which our senior learners feel most is, I will have to down level. You have built a hard-earned stack and restarting feels wrong. The real challenge underneath all four is same. It is picking the right path in AI. And the good news is that you don't need to down level at all. You can start exactly where you are. Here's the Here is how we map that path. Thinking of up leveling curve with five stages. The first two stages are augmentation. Stage one is working with the large language models. Stage two is using AI co-pilots to multiply your everyday productivity. The next stage are transformation. Stage three is building real AI agents and generative AI application, which is exactly what Shurit is going to show you today. Stage four is building on top of advanced machine learning models. And stage five is building modern learning models yourself. And that is the most important one. The point of curve is simple. There's no one size that fits all. The goal is to build your own AI quotient from wherever you stand today. All right. What does this translate into in terms of roles? On the transformation side, where most of the hiring is happening, it is your domain plus AI skill. That means AI-enabled softwares, AI-enabled product managers, AI-enabled engineer managers, technical program managers. Further along, the curve is it's becoming AI engineering and the modern machine learning language. See, we have programs that are mapped onto that curve. You do not have to guess which one it fits. When you see here, the first is transformative Gen AI and agentic AI paired with our interview lab. This covers generative AI, agentic AI, the interview preparation in your own domain. If you're not sure where to begin, this is the place to start. The second is agentic AI accelerator. Yeah. The second is agentic AI accelerator, again with the interview lab. This is focused on agentic AI, industry relevant projects, and interview preparation in your domain. It is for the people who already have some AI exposure and want to build something strong in the real world portfolio. The third is basically the flagship ML with the interview lab, which also includes agentic AI. This is for the people who want to fully transition into a machine learning role, which is more relevant to you. Now, this is where we are, where we are different, and it matters for a room as senior as this one. We do not run one generic course. We customize across 18 tracks, as you can see. See, if you are an experienced individual contributor, we have specific tracks for backend, front end, full stack engineering, for machine learning, data engineering, and data science, for cybersecurity, site reliability, and DevOps, even embedded software, test engineering, cloud, Android, iOS, and business intelligence. So all this. If you are in management, we have tracks built for engineering managers, product managers, and technical program managers. And we support people early in their engineering careers as well. The interview preparation and the career support are customized to your track, not handed to you off a shelf. On the preparation itself, here is what the interview lab gives you. You get at least 15 mock interviews simulated with hiring managers with detailed written verbal feedback. You get live sessions from tier one experts, just like Shraddhir. You cover data structures and algorithms, system designs, and domain specific preparation. And you get a full set of career services, resume optimization, LinkedIn masterclass, behavioral interview strategy, regular check-ins to catch anti-patterns and offer negotiation strategies. With that, not just this, with that, we have an outcomes. We work with more than 200 hiring partners in India. When they have demand, we make performance-based referrals and share their profile of our strongest learners. I want to be straight with you. This is based on performance and demand. We do not promise placement at all. We prepare you to earn it. A quick word on time, because that will matter. So you can see that each path only asks of you. The transformative Gen AI and agentic AI with the interview lab runs about 3 plus 3 months, and it is the right place to start if you are unsure right now. The agentic AI accelerator with the interview lab runs 12 weeks plus 3 months. And it is built to get you AI enabled, which is where the bulk of AI jobs are right now. It does exact some Python. It does expect some Python and basic AI skills coming in. Flagship ML with interview labs, run about 6 plus 4 months, and it is for full transition into an ML role. On the transformative Gen AI and agentic AI with the interview lab ranges from 1 to 2.5 lakh. So this slide is very important. The agentic AI accelerator with the interview lab ranges from 2 to 2.8 lakh, around that. Flagship ML with the interview lab is around 3 lakhs. And there's an offer available on it. All of these include access to our 18 tracks, all the 18 tracks, which I mentioned earlier. We also have some financial side flexibility. There's financial through EMIs, there are alumni and other scholarship running right now. And certain programs carry a refund up to 50% under specific terms. That means whatever prices are written, they will slash directly 50. You can enroll now and start when it suits you. And placement assistance through our 200 plus hiring partners stays with you throughout. If you give us a chance, we will build you a roadmap. If you give us 30 minutes, we will build you a roadmap and a return on investment view that is specific to your profile. I'm going to launch one more poll. I want to know how many of you would like one-to-one consultation so that we can map a proper roadmap for you. Please mark your answer while I hand it back to Sharit. Sharit, over to you. Bring this home.
Um,
Yeah, I'm stopping my
okay, I'm going
screen.
to take the screen share, with. Okay, so the next thing that we want to look at is building a RAG pipeline with LangChain. So the three key LangChain abstractions that make designing a RAG simple is your LLM, your retriever, and the memory, right? So LLM is your language model interface, retriever is the vector store for document retrieval, and memory is the conversation memory agent. And so really, when you set up a RAG system, the RAG-based code is fairly specific. You have your LLM, you have your vector DB, you have your retriever, and then you have this chain that essentially takes the user query, retrieves the information, and generates a response, and stores the responses in memory for enabling continuity in a conversation. What does that mean? Can folks mention in the chat what adding this memory is equal to memory, like what does this do? So we have memory as conversation buffer memory. What does this do? Yeah, it maintains the exactly as I think some of you are saying, it maintains a cumulative chat or the conversation summary associated with what is going on so far, such that it maintains a certain level of continuity in the conversation. So that's the memory part. Vector-based DB also are very robust to spelling errors because they deal with semantic similarity and not like just keyword or string-based matching. Spelling errors are handled correctly. Lowercase queries work just fine. Again, semantic meaning is the same for capitalized or lowercase things. And contextualized references. So what did she do before? Correctly answers questions about this specific person. Again, this is because of that memory thing, right? Okay. Um, a lot of LangChain based code is in this LCEL format. LCEL stands for LangChain Expression Language. It's like a very declarative YAML based approach to defining RAG based pipelines. So Um, it's you can use that, but it also works just as well with your typical Python-based APIs and Python-based frameworks. So, so that was just how you assemble a RAG-based system. How would you debug a RAG-based system? When the RAG-based system fails to find the right information, we need to understand how to really diagnose this stochastic system. A lot of these LLM-based systems are stochastic in nature. Why are they stochastic in nature? Because LLMs by definition are a next token predictor machines. They don't have a specific, like if you ask an LLM the same question, there's a chance that it might generate a response which is factually correct and everything is nice, but the wording of that response might be slightly different than what your response was one step before for the exact same question. And so, how do you debug all of that information? Um, Simple things that you can do is enable callbacks. So LangChain has standard output callback handler. What that essentially is that it has the ability to surface all the stack trace associated with the LLM call, what happened inside the LLM, what went to the LLM, what was the um, um, input query, what was the output query, if the LLM, what was the intermediate steps that the LLM took. All of that you can surface using the callback. You can examine the retrieved context. So you can see, apart from the user query, what was the thing that was attached to the user query to augment it in your RAG-based application. And you can analyze the prompt to see exactly what the model sees. So, for example, who received the prestigious IoT Innovator Award reveals a retrieval failure. Maybe the expected answer was this, but the actual answer is I don't know. And in a RAG-based pipeline, it's it's important to identify if the failure point happened at the LLM stage or at the vector DB stage or at the retrieval stage. For example, if you're going to chunk documents, but if there is no chunk overlap, so let's say you chunk words 1 to 100 in one chunk, and then you chunk words 101 to 200. But let's say there was some important context which stayed as a combination of words 100 through 105. You have lost that context now because you have like done this hard split on the words and broken them into chunks. In order to preserve that context, you have to chunk your documents better. And that problem is a retrieval problem, not a LLM based problem, right? And so that's one type of problem. The other type of problem could be an LLM type of problem where essentially all the retrieved chunks are also correct, but you get, let's say, hallucinated responses. Then, so it's important to identify which, at what point in the stack or at what point in the framework is the error happening. Um, Fixing some of these retrieval-based issues, which are the most common issues in a RAG-based system, is increasing the chunk count, improving the chunking strategy, using entire documents if your documents are small enough and if your LLM is capable enough. Um, and so if you increase the chunk size to around like a little bit more, it correctly surfaces the relevant documents to answer the question at hand and then identifies Maxine as that IoT award person. And finding the right balance between like how many documents to retrieve, how much should the chunk overlap be, should the chunking split be like 1,000 characters, 1,200 characters, should the overlap be 200 characters? All of these things are designing Gen AI applications is as much of an art as it is science. And therefore, a lot of the development is an iterative design process. You have RAGAS is a framework, yes, as some of you are saying in the chat. RAGAS is a framework that can also help. Um, So finding the right balance between like how to manage this context, how to manage model performance is an iterative process. So more context will give more information, reduced missed answers, and more comprehensive responses. But then for each of those things, you're paying a cost. The cost is for better information coverage, you are going to increase the latency. For reducing missed answers, you are going to pass in larger and larger context, and that can make the LLM confused as to what exactly are we doing, and also higher token costs. Um, so chunk size tuning is what I was mentioning. Retrieval count, continuous CI/CD pipelines are some of the techniques that you can borrow. Like CI/CD is something which is done typically in the DevOps world already. So that concept has been borrowed from the software engineering world. But these hyperparameters associated with RAG and tuning them is essentially a part of the process to design an optimal system. And so some of the techniques are hybrid search as opposed to only similarity search. So you combine similarity search with the traditional keyword-based search. Use a re-ranker after the retrieval. So once the retrieved chunks are there, you rank them again to surface the most relevant ones at the top. And query expansion. So once the user asks a query, generate some additional similar queries that might answer a same type of question. Okay, so in a RAG-based system, what is the most common trade-off when you increase the number of retrieved chunks significantly? Correct, right? It's true because if you increase the chunks, you're going to have higher context, so higher chance of finding the correct answer, but also more token cost, right? Okay, so in our let me quickly okay, so in our demo, we are going to look at setting up some documents, you creating a vector DB using Chroma, building a chat interface, and then testing and iterating, right? So let me see if I think I lost my runtime, and so I might not be able to do this. Give me one. We'll still run the code and go through the notebook. It's just that I lost my runtime, and so it's not. I cannot. Or it has to be this way. I see. Um, okay, I think it's updating the thing. So anyway, so the very first thing that we are going to do is Um, we are going to be building a question answering agent that is an expert knowledge worker to be used by employees of this internal company, an insurance tech company, and we want to develop an accurate agent that should be low cost. And so we'll build a simple RAG-based pipeline. So again, we are going to be using LangChain to do so. We are going to use OpenAI's embeddings to convert the text into an embedding, and then yeah, those are the main packages. Some of these other packages are just other peripheral packages that you need. You need an OpenAI API key for accessing OpenAI's models. Um, Here, all I'm doing is I'm taking in all the imports that are relevant. So this is that document loader I was talking about. This is that chunking strategy where we chunk our documents based on character. You have multiple different text splitters available from LangChain based on the chunking strategy that you want to use. For example, yeah, so see, if you have a HTML document, you have HTML header text splitter. If you have a markdown file, it uses markdown's properties to chunk the thing appropriately. If you have simple text, then you can use this. And so you have multiple different um, chunking strategies that you can embed. You also have documents. So if you have a PDF document, HTML, Markdown, code files, and so on, you can specify those. OpenAI embeddings, again, is just OpenAI embedding for model integration. And chat OpenAI is essentially importing GPT models into the uh, working environment here. Let's see if okay. These are again just some basic Python, classical Python packages. This is memory that we said previously, and this is the vector DB that we are going to be using. Okay, so we are going to be using GPT-4 Mini and initialize our vector DB with this vector DB name. Um, we read in the documents using LangChain's loaders. So essentially we have this knowledge base folder and we have these company contracts, employees, and product documents in there. And we take those documents and convert those documents into this documents object. And now we use a text splitter. So we take 1,000 characters and each of those 1,000 characters are then one chunk and we do so for every single document, right? And so what we have done is that, um, again, forget this particular response, but earlier when I ran this, we went through all the documents in this knowledge base here, which was company information, all of this was, let's say, broken down into um, like 1,000 characters here, 1,000 characters here, 1,000 characters here, and so on. Same thing for this file, same thing for this other file, and so on. And you do this across all the different documents that we have, right? And so once you do that, you get approximately for, 413 chunks from like those 13 or so folders that we have. And so all that we did here was just split those documents that I just showed you in a series of chunks. Okay. Um, Now the next thing that we need to do is we'll be mapping each of these chunks into a vector that represents the meaning of the text, known as an embedding. And we'll be using OpenAI's embedding model to do this. So you can use more complex embedding models like BERT and so on. So that's another option. So choosing an embedding model is also a iterative piece that you may want to work with. But in this case, we are going to use OpenAI's embedding models. They come back with a 1,536 dimensional vector representation. So, and you have other embedding models that you can use as well. That's a choice that is up to you. But once we have that embedding model, once we have those document chunks, these ChromaDB has a method from documents that says, give me a list of documents and give me a list of, and it says document, but what it expects is a list of like chunks. And for each of those chunks, I'm going to use this embedding model to convert them into an embedding and then store them um, in a persistent directory that is this DB, right? We called it vector DB generically. we call it a generic vector DB thing. So it's going to persist, and then you will see a vector DB object that comes here once you run that code. So once you run that, it creates 413. So vector store created with 413 documents. Um, so there are 430. So once you um, test that, so you can essentially look at the lengths of all of these embeddings in our vector DB. So you have 413 documents with each of them being a 1536 dimensional vector. So it just looks like each of these sample embeddings essentially look like some vector like this, and so on, right? So we have 1536 numbers like this. Okay, so that's your one sample embedding, and you have um, like another one, and you have like 413 such such vectors here corresponding to our documents. And so one thing that we can do is uh, we can essentially convert these documents and represent them as a graph in a 2D space. That's where we have used these TSNE plots, and we have taken those 1536 dimensional vectors that we identified previously and mapped them onto dimensions. So what this thing is really doing is we know that our vector DB has these distinct documents that have information about products, about companies, about employees, contracts, and so on. And so we are going to see if the way those vectors are represented is are those vectors that are created, do they cluster meaningfully in a meaningful manner? And so what I'm doing here is just taking those vectors that we created in our vector DB, right? And taking those vectors and plotting them on a 2D graph. And so what is happening here, as you can see, is that all of these red dots are contractual information, and clearly they are in a cluster. There's a small cluster next to it, which is products. You can see why contracts and products are somewhat similar, because contract is typically associated with an insurance product. So, for example, um, yeah, so contracts, digital health integration, wearable device connections, Fitbit, Apple Watch, some information about that. And then product, you can see why Fitbit, Apple Watch, and so on and so forth is also, it can be confused with the product, right? So this blue thing is product. Um, the green thing is a completely different cluster here. And you can see why. This is a employee information, so annual performance, history, salary, their name, date of birth, very different information than what is happening here, right? And then you have this company specific documents in yellow. So that's our two-dimensional representation. You can do the same thing in 3 dimensions. Here, as you can see, there might be some confusion. We have marked them with different colors, and so it's kind of visible. But otherwise, if all of this was just one color, you could only identify two clusters, right? This cluster here and this cluster here. So sometimes it's helpful to map things in 3 dimensions, because as you can see, the yellow thing was not even correctly visible, but in 3 dimensions, this yellow uh, company cluster is more visible as a bubble of its own. Even the red one and the blue one are, I think, more visible as a bubble of their own, right, in this 3 dimensional plot. So sometimes this 3 dimensional mapping is also very beneficial. And so now, uh, time to use LangChain to essentially create our RAG-based system. So we saw in the slides, essentially our RAG-based system code is fairly a small piece of the entire architecture, which is true of many ML-based systems. A lot of the um, code is the infrastructure surrounding around all of these applications. And so this essentially is our LLM that we are going to use, GPT-4o Mini. Um, you can set up this memory to essentially summarize our conversation. Retriever is our vector store that we have built, and then putting it together is essentially just creating this conversation chain that you can then use the invoke method on to get the RAG system going. So let's try with the simple example. So please explain what ensure LLM is in a couple of sentences. We pass it to this conversation chain. It uses this LLM, uses this retriever, and stores the response in the memory to summarize. So the result is that Insure LLM is an innovative insurance tech firm founded in so and so, developing this or that, and um, it has 8 comprehensive platforms designed to connect with customers and insurance and streamline insurance processes, right? Um, so this is again just setting up the whole memory and using a chat interface like in Gradio. This just creates a chat interface at the bottom. Not super important, but what essentially happens behind the scenes. So who received the prestigious IIoT award in 2023? Um, so essentially what happened here is it started this conversation retrieval chain, um, and it was using this system prompt. Use the following pieces to answer the user's question. If you don't know the answer, just say don't know. Don't try to make up the answer. Um, and so this was the context that was retrieved. So the um, retrieval came back with these types of information here, and all of this, and the answer is I don't know. So basically, what this is making us realize is that, okay, we have a certain level of documents that we have retrieved. So our retriever, I think, retrieved some top K documents, maybe 3 or 4 that we mentioned earlier, right? Somewhere earlier in the code. And um, retrieving just those documents, you are not able to get any information about this IOTY award based on the documents that we just retrieved. If you actually, sorry, this response actually went away. If you actually retrieve more documents from your vector store, and if you run the entire chain again, and if you ask that same question, it will actually come back as we saw in the slides, right? It will actually come back with the correct answer that um, this Maxine was the award recipient, because the default was 3, we improved that to 25, and so it will come back with the actual answer. So that's really all that I wanted to cover in the demo today. I will upload while I answer Q&A. I'll see if I can upload this and get this thing to actually run. But let me quickly go back to the slides. This is right. So these are some of the things that you can do. One caveat that I wanted to mention is stuff like this we typically cover in like what I showed in 1 hour right now, we cover typically in 4 hours of class content with the 3 to 4 hour another follow-up session to go over the extra questions that you may have. We focus on each of these concepts of vector DB, embeddings, LLMs, retrieval, and how to optimize, debugging, evaluation. So this was just a flavor of how we do things. And so with that, I wanted to open up to Q&A.
Thank you, Sharit. Thank you. That was fantastic. I hope everyone enjoyed the demo and got a practical understanding on how these systems are actually built and deployed. We already have a lot of questions coming in through the chat. I have been answering some of your questions live in the Q&A panel. For anything you would like Sharit to answer directly, please drop into a panel now. We have few minutes, so let's take us the most useful ones. I also
Hmm.
have jotted few of them down. If let me just share my screen and then we can take it from there. Just one moment. All right. So till I share my screen, any of the questions that you would want to answer from the chat, Sharit?
From the chat, yeah. So how do we measure accuracy of a RAG-based application? So typically, RAG-based applications have um, metrics like precision at K, recall at K, and accuracy. So the accuracy is measured based on how many retrieved documents that you have. First of all, accuracy is the answer correct, right? You have some ground truth questions that you know the answer to, and you test if your system is able to get the answers to those ground truth questions. Second, you can see how well your retriever is performing by thinking about metrics like precision at K, recall at K, F1 score, and so on. Um, you have frameworks like Ragas, which enable you to do this, and you have frameworks like Langsmith to enable observability and evaluation framework. But those are some of the things that come to mind when evaluating the performance for RAG-based system. Uh, can't How do we handle unstructured data properly? So yeah, as I said, handling unstructured data is one of the key pieces in making sure the retriever is able to chunk the documents and retrieve the relevant chunks. LangChain has integrations for HTML, like leveraging the document structure is one of the most important things that you can do to handle unstructured data. And so you would chunk a coding document, like a piece of code, very differently than the way you would chunk a storybook, right? And so to handle unstructured data, you will have to leverage the different APIs, integrations that exist within these frameworks, or design one or design a custom chunking strategy on your own if you have more context on how this text is structured to make sure that the you are enabling as much information into a chunk that is and making that chunk context aware, so to speak. Um, okay, Mohit, I can take your questions.
Yeah, let's do that. So the first question is there are many possibilities. You hopefully you can read the question as well.
Yeah, so there are many possibilities that documents can be very large. So do we send that much info to an LLM, and isn't that extremely token exhaustive? Absolutely, yes. There is a possibility in that case. You will have to chunk the documents smaller and smaller and um, try to see that balance between large number of chunks and making an LLM super expensive versus small number of chunks and LLM missing out on critical information. That is as I said, this designing these systems is as much of an art as it's science, and that this is the art part of it, which is this iterative hyperparameter fine tuning is a part of the process. One question, what is the underlying tech stack for programming language upon which these open source LLM are based? Also, kindly let me know the algorithm so that as a developer, we can explain to potential customers. So as I said, typically these tech stack is underlying tech stack is any like you have integrations with Java. Python is by far the most popular, but you also have integrations with Java and Go in some cases for building applications using LangChain, LangGraph, Crew AI, um, and other agentic frameworks that you can use. So I think the first part of your question about the tech stack and programming language. Another open source package that you can use is Olama. Olama also hosts a lot of these LLMs, open source LLMs specifically, that you can integrate with, again, Python and Golang and Java. And also kindly let me know the algorithm so that as a developer, we can explain it to the potential customers. So there is no one specific algorithm, right? That RAG is a paradigm. It's not a specific algorithm. And so you should the algorithm that you explain to the downstream customer will be highly dependent upon what you are designing in this RAG-based application, or if at all if it's a RAG-based application. So it's not necessarily an algorithm, it's a modular design that borrows aspects of LLM with aspects of retrieval, with aspects of keyword-based search, and generates a response. So metadata is an alternative for faster semantic search. Who will tag the metadata? Is it a manual process or will LLM tag it? It can be both. Yes, but manual human in the loop tagging is one of the cleanest, painful and slow, but the cleanest, most reliable one-time thing that you will have to do to make your retrieval really, really strong. Now, that being said, you can of course use LLM assisted methods to create tags for the metadata. It's just that the tagging is not done automatically within a RAG-based system. You have to kind of do it and let the LLM know that, okay, look, this is the metadata associated with this document. Use this. Is this ready-made structure code for RAG or only configuration we have to change? It has all the pieces, yes, and it's most of the RAG-based systems will have one or the other aspects of what I showed today. So the code is there. It might have some other bells and whistles. For example, our thing only does one type of chunking. You may have a RAG-based system that does multiple types of chunking based on which document it's seeing. So you might have complexity there, but overall, yes. If we decide not to use OpenAI and instead use free alternatives, are there any providers from which we can obtain API keys and process requests? Yes, I mean there are, as I said, Olama is hosts a lot of different open source LLMs. There are some models like DeepSeek, Grok, um, which GPT OSS is another open source one. But again, I guess that's OpenAI. The Llama series from Meta is an open source LLM. Now, that being said, those LLMs perform slightly they underperform slightly when it comes to state-of-the-art models like Claude, like Opus and Gemini and so on, and GPT-5 and so on. But those are some of the alternatives. And how do you evaluate these? Hopefully the implementation is straightforward. It's just changing the model name in that one line that I showed you in the code. How do you evaluate this thing? Again, you create these ground truth data sets, change the model, and see if your outputs with one model and the next model are similar. Track metrics like accuracy, precision at K, recall at K, using the RAGAS framework. Use Langsmith for creating A/B testing type of experiments and seeing which parts of the model degrade if you change from LLM1 to LLM2, let's say. Is vector embedding very new tech or has been used for a long time? The vector embedding was previously so vector, the concept of a vector, so word to vec type of models have been existing since the last 10 years, maybe even 15 years. So the technology itself is not new, but with the advent of Gen AI and LLM, it has just become extremely popular. And so the use case of this technology has exploded in the last 2 to 3 years. ChatGPT came out in November 2022, right? Today is June 2026. So like 3.5 years almost. Um, and it's just that with the advent of LLMs, all of these peripheral things like GPU processing and embeddings and image processing and image embeddings, they just became more and more popular. Um, so the algorithm itself might be old, but the prominence of it or the popularity of it is fairly new. Can't can't we create virtual environments or Docker with specific version installations and use that itself? Yes, you can absolutely do that. Absolutely. In fact, in production setting, that's what you would do. Um, auto agentic Auto-agentic RAG and normal RAG difference. So, uh, what is an agent? Can someone mention in the chat? What is the simplest definition of an agent? An agent is nothing but an LLM plus tools. So, if an LLM has access to a particular set of tools, that's LLM plus tools. That's your agent. Agentic RAG is nothing but a RAG-based system where the LLM, apart from having this vector DB and retriever and all of these things, this LLM, apart from being a pre-trained LLM, also has access to, let's say, APIs. So let's say you have a series of latest news information, like your vector DB has um, latest let's just say your latest sports news, right? Let's say it's the latest cricket news that your vector DB is storing, and you also have weather API as a tool integrated into your LLM. And now you ask your RAG-based system on this vector DB thing. It's showing me on the latest sports news that tomorrow there is match between Team A and Team B in Bangalore. Um, what is the weather tomorrow in Bangalore? Should I buy the ticket? Because if it rains, I don't want to buy the ticket. This agentic RAG will be able to answer the question, right? Because it will go to the vector DB, say, okay, tomorrow's match is between team A and team B. The user is asking about the weather. Let me quickly go to the weather API and look at the weather prediction for the next 24 hours. And it will say, okay, look, the tomorrow match is between this and this. The weather is so and so with a probability of rain of 75%. There's you take your pick. The ticket is like 1,000 rupees. You want to spend that and get the thing. That's your agentic RAG. Normal RAG won't have access to that tool, the weather API tool that I gave in this particular example, and that's agentic RAG.
All right. Wonderful. If anyone has any other questions, they can leave in the chat. We'll just wait for another 1 minute, probably 3 seconds, let's say. There's one question from Manish, if you can see.
Hmm. Can we? Is it in the?
Yeah, just 1 second. I'll just copy paste it here itself so that it will be easier for you. Question number 9.
So in RAG, we retrieve documents from vector DB. Those are fed to LM to. Yes, yes, that is exactly what is happening. So we retrieve those documents from there and then add them to the prompt. Um, and then send that to the LLM for generation.
Everyone is trying to reduce their tokens nowadays. There's one question on reducing token as well, if you would like to take that.
Reducing tokens. Um, yeah, I'm thinking how to reduce token usage by RAG. Um, One way to do so would be with like a very it's a broad question. One way to do so would be with a better chunking strategy and a better retrieval strategy, such that you are chunking the documents even more, such that instead of having 1,000 word chunks, you have, let's say, 200 word chunks, and you retrieve only a small part of that. And so the entire context is reduced, and therefore, by definition, tokens are reduced. Again, now you lose the you might risk missing out on certain information, but that's the price you have to pay. LLMs are expensive systems to run, and yes, throwing more tokens at the problem is going to improve the response, but then it also makes it more expensive. That's the constraints that you have to operate by.
Wonderful. I think that's all the time we have for today. Thank you everyone for joining us and spending your evening with us. And thank you for the quality of your questions. The participation tonight has been excellent. And a special thank you to Shurit for sharing his insights and experience. Thank you so much. I hope today's session gave you a practical understanding of RAG, LangChain, and how modern AI applications are being built. For those who have booked a slot with us, our program advisors and experts will be in touch. Thank you once again. We'll see you on the other side of upskilling. Have a great evening. Thank you.